All right, I forgot to record the commentary on this, but this is pretty much it. All right, so let's take a look at a calculation here next. A solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Barium sulfate precipitates. Calculate the ideal yield of barium sulfate. So the first thing is we need a balanced chemical equation showing this reaction. So we'll need to write out the formula for barium chloride. What is the formula for barium chloride? BaCl2. Sodium sulfate? Na? Na2SO4, good. Barium sulfate? BaSO4 plus NaCl. NaCl is Na2Cl2 or NaCl? NaCl, and then we'll put the 2 in the front. And so this would be, it's just a 1-to-1 mole ratio. So if we have 3.18 grams of barium chloride, what we'll do is we'll go from grams of barium chloride to moles of barium chloride, grams of barium chloride to moles of barium chloride, and then moles of barium chloride to moles of barium sulfate, 1-to-1 mole ratio, and then to grams of barium sulfate. So we have to calculate the molar mass. They did it for us here, so we'll just use theirs. They calculated the molar mass of 208.2. This unit missing here, the unit should be grams. You know, the mass, if we're looking at a mole of these, then the unit will be grams. If we're looking at one individual formula unit, then the unit would be what? U. Good. All right. And so the gram to mole conversion here. So this is what they do here. They'll go 3.18 grams, and then they'll use the molar mass here. 1 mole of barium chloride formula units weighs 208.2 grams. So the grams of barium chloride cancel. That leaves us with moles of barium chloride. We need to get rid of moles of barium chloride. Here we could use the mole ratio. It's a 1-to-1 mole ratio. So 1 mole of barium sulfate to every mole of barium chloride. And so then the moles of barium chloride cancel. That leaves me with moles of barium sulfate. And then we could use the molar mass. They gave us the molar mass of barium sulfate here, 233.4 grams per mole, and that gives us 3.56 grams. This is the what we call the theoretical yield here. That's how much we should get. But in this experiment, the actual yield that they got, and this varies from experiment to experiment, you know, the actual yield is what you actually got for that experiment for that day. And so this is given, and so you just weigh it and see how much you got. So they got 3.37 grams. So that means they lost how many grams of product? 0.19 grams they lost. You see that? And so that 0.19 grams turns out to be a 5.3% loss. Or in other words, this is 94.7% yield. And this is called the percent yield. So, yeah, this is still pretty good. You know. And so a little bit was lost. It's hard to avoid that loss. Even if you expect 100% yield, there are no side reactions. There's no incomplete. This is a complete reaction. This is a pretty good driving force here. Solid sodium nitrate decomposes into solid sodium nitrite and oxygen gas upon heating. One set of reaction conditions gives a 95% yield. So let's go ahead and write the formula. What's the formula for sodium nitrate? NaNO3. And what they did was they heated. This doesn't decompose into the elements. You know, we saw earlier some decomposition reactions will decompose into the elements. In this case, they tell us. You know, it depends on how hot it is and other conditions. And so the products that it decomposes can be altered depending on how hot and other factors, pressure, etc. And so this decomposes into sodium nitrite. What's the formula for sodium nitrite? NaNO2 plus oxygen gas. Now we could have a fraction here because we have 3 oxygens here. 2 plus 2 is 4. So if we multiply this one by 1/2, that would work. Or if we double everything. So let's go ahead and double everything here. So that gives us 6 oxygens here. 4 plus 2 gives us 6 oxygens here. So this is an example of redox decomposition here. Because oxygen likes to be at -2, and this is, the charge here is on 0. If you have 2 oxygen atoms and the whole thing doesn't have charge, then the charge is 0. So the mole ratios here, let's see. Solid sodium nitrate decomposes to solid sodium nitrite and oxygen gas upon heating. One set of reaction conditions gives a 95% yield. So we expect a 95% yield. And so we'll just say is typical. Of course, this can change, you know, depend. But typically, when you do this, you get a 95% yield. That doesn't mean you're always going to get a 95% yield exactly, but since this is the ballpark, we'll use this as a guide for our prediction here. What mass of sodium nitrite will be produced by the decomposition of 1.5 grams of sodium nitrate? So what they're asking us to do is they're just going to ask us to predict what the yield should be. And so what we're going to do is first we have to calculate the theoretical yield. And then what they want is they want the actual yield. And so here they're asking for the actual yield of sodium nitrite. So what we're going to do is we're going to use the equation. The percent yield is equal to the actual yield divided by the theoretical yield times 100%. And so we could use this to calculate the actual yield here. And this is predicted, you know, whether we get that or not. It's going to depend on other factors. And so what they're doing here is, okay, first they're going to calculate the theoretical yield. So we're going to calculate theoretical yield. We calculate the theoretical yield by stoichiometry. And so looking at the stoichiometry here, we go from grams of sodium nitrate to moles of sodium nitrate. Okay, because we have how many grams? 1.5 grams of sodium nitrate. So in theory, how much sodium nitrite can be produced from this? And so we'll start off with 1.50 grams of sodium nitrate, convert that to moles of sodium nitrate, go from moles of sodium nitrate to moles of sodium nitrite. It's a 2-to-2 or 1-to-1 ratio here. And then convert that into grams of sodium nitrite. They call ideal, I'm just going to call it the theoretical yield. That's how much we should form. And then we're going to do one more calculation to get the grams of sodium nitrite actual yield over here. There are 2 ways we could do it. We could do a separate, or we could use a conversion factor at this step here. So they give us some data here. They give us the molar mass of sodium nitrite here, and the molar mass of sodium nitrate here. So if we start off with 1.5 grams of sodium nitrate, then let's go ahead and calculate the theoretical yield here. Theoretical yield is up to here. And then we can do one extra step here to get the actual yield. And so they do 1.5 grams of sodium nitrate and then convert it to moles using the molar mass, and then convert it to moles of sodium nitrite, and then convert it to grams. So we go grams to moles, moles to moles, moles to grams. Okay, once we get that, this is the theoretical yield here up to this point. And so what they're going to do is they're going to use the 95% as a conversion factor. The 95% here means that for every 95 grams of actual yield, we have to have 100 grams of theoretical yield. So they convert the percentage into a fraction here. And so we can use that as a conversion factor here. So for every 100 grams, we only get 95 grams. That would be expected. So the expected loss here is 5 grams. The other way we could do it is we could stop here with the theoretical yield and then just plug it into the equation for percent yield. And we know that the percent yield is 95%. This is probably better to use the percentage as a conversion factor here. And so let's calculate both of those here. So I'm going to calculate the theoretical yield. It would be 1.5 divided by 85 times 69. And so the theoretical yield that we calculate up to this point is 1.217 grams. So about 1.22 grams. And then since we only have a 95% yield, let's go ahead and calculate this. It's going to be 95 times 95 out of 100, which gives us 1.156 grams. So we predicted we should have gotten 1.217, but since we always lose about 5%, then the actual yield is going to be 1.156. This is our theoretical yield. This would be our actual yield. Now, rounding it to the number of sig figs, we can't be so precise because this is only 2 sig figs here. Since that's only 2 sig figs, we're going to round this to 1.2 grams. So anyway, if we were to do this using the correct number of sig figs, this is why I carry extra sig figs. Our theoretical yield is 1.2 grams. Our actual yield is 1.2 grams. So did we lose any? No, it appears we didn't. And so we need to carry extra digits to see that we actually did lose some in this particular example. All right, in both of these problems, we base the theoretical yield on the reactant here, sodium nitrate. You know how many grams we had to begin with, 1.50 grams of sodium nitrate. In the previous problem, we base it on barium chloride. You know, how many grams of barium chloride did we start with? But we completely ignored the sodium sulfate in the previous problem. And so the only way we can completely ignore the sodium sulfate is we have to make an assumption. And the assumption is we assume that we have excess. In this problem, we have to assume there is excess sodium sulfate. we assume that there's excess sodium sulfate. That means all the barium chloride can react. But what can happen is, what if we don't have enough sodium sulfate to precipitate out all the barium? If we don't have enough sodium sulfate to precipitate out all the barium chloride, then we aren't going to get this kind of yield. And so if we can't assume that there's excess sodium sulfate, then what we have to do is we have to do this. We have to do what's called the limiting reactant problem. In the limiting reactant problem, reactant first totally consumed in a reaction is the limiting reactant, determines the maximum yield possible, and so excess reactant. And so in other words, we have an A plus B type situation in which one of these is limiting, the other is excess, or it's stoichiometric. So we have three possibilities. Possibility one is it's stoichiometric. That is, we have stoichiometric quantities. What stoichiometric quantities means is we have just the right amount of A and just the right amount of B to react. Two, we have excess, let's say B, this would be like in the previous problem. If we have excess B, then A is limiting reactant. And B is the excess reactant. Or three, the next possibility is we have excess A, and B is equal to the limiting reactant. And so this is like an example of this would be if you had to build a bicycle. And so each bicycle would need like a frame plus 2 wheels. And this is the stoichiometry of it. If you had one frame and 2 wheels, then that's stoichiometric. But let's say you had one frame and 4 wheels. If you had one frame and 4 wheels, could you build 2 bicycles? No. That would be number 2. Or let's say you had 2 frames but only 2 wheels. How many bikes could you build? Just one bike, right? And that would be like 3. And so this is the stoichiometry. The stoichiometry is given by the balanced equation. That would be like 1 here. But 2, we said if we had excess B. So let's say we had 4 wheels and 1 frame. Or 3 would be like 2 frames and 2 wheels. That's going to limit the number of bikes we can form. So we have to consider these factors when we look at reactions, because the reactions are going to behave in much the same way. So, yeah. Sure. So here's stoichiometric. Here we have 1 carbon needs 2 oxygens to form 1 CO2. This is stoichiometric. Now, if we take 1 carbon and 1 O2, then it should react nicely. So if I have 3 carbons, how many O2s do I need? Stoichiometrically. Well, if I have 1 carbon, I need 1 O2. If I have 2 carbons, I'd need how many O2s? 2. If I have 3 carbons, I'd need 3 O2s. So I'll take 3 carbon atoms here. Carbon's normally a solid, so they vaporize this using some laser or something, which you can do. You can vaporize carbon atoms off, let's say, graphite using a laser. And so now we have these carbon atoms in the gaseous state. And how many O2s do we have? 2. Is that enough? No. And so what we say is that we have excess carbon atoms, but we have limiting O2. And so O2 is our LR. LR stands for limiting reactant. Carbon is our excess reagent. Usually we just write XS, the letters. So that means we're going to have only 2 CO2s that we can generate from this because we don't have enough oxygens. And so this is like bicycle. The carbons would be your frame, and then the O2s would be like your wheels. So we have 2. And so we could build 2 bicycles here. But the third frame is not going to have any wheels. And so this is what we call leftover or unreacted excess reagent. So this is summarized in a table. Skip that. So how do I solve it? There are different ways that people solve this. There's the comparison of moles method and the limiting smaller amount method. I use this method here, so I'm going to skip this, the previous slides, and go straight to this one. The smaller amount method, the smaller amount of product. Which one yields a smaller amount of product? So if we go back to this here, what we do in this calculation is calculate how many CO2s can we form with 3 carbons. With 3 carbons, we can form how many CO2s? 3 CO2s, if we had enough oxygen. And so what we do is we assume there's plenty of oxygen. If there's plenty of oxygen, then in theory, we should be able to build 3 CO2s. But if we have only 2 O2s, well, how many CO2s can we form? Only 2. So this is like the bicycles. If I have 3 frames, I could build 3 bicycles. But if I only have 4 wheels, 4 oxygen atoms, then I can only build 2 bicycles. And so the smaller amount will win. The smaller amount will be 2. And that will be our theoretical yield. And so our theoretical yield will be 2. Our theoretical yield will not be 3 because we don't have enough wheels or oxygen atoms to build that. So we're going to take a look at this. There are 2 types of calculations. One type of calculation is we want to determine this. So actually, let me go ahead and so for a limiting reactant problem, Um, these are the steps I usually do for this. Let's say I have A plus B. All right. So the first step I do is I calculate A plus B yields C. I calculate the yield of C from A, assuming excess B. Okay, then 2, you calculate the yield of C from B, assuming excess A. Then 3, determine which 1 or 2 gave the smaller yield. It's the smaller amount. Okay, that would tell us what the limiting reagent is. The limiting reagent gives the smaller amount, which I'll just call yield. And that smaller yield is equal to the theoretical yield. We can't produce the higher yield because we would run out of parts. That is, A or B would run out. Okay, and the reagent that gave the larger yield reagent is just the reactant in this, and there are two reactants, A and B, and we could have numbers here like XA, YB. It doesn't have to be 1 to 1. And so typically in a calculation like this, we were after the theoretical yield. Now, percent yield is a different story. We might calculate the percent yield. So there are a number of things we could do here. So for example, we could go here and if actual yield AY is given, then can calculate percent yield. So if we know, how much we're supposed to get, let's say we're supposed to get 100 grams, but you do the experiment, and let's say you didn't want to hassle with getting every last drop or every last crystal or every last bit of gas, bubble of gas from this, then we would have lost some, and then we can figure out how much we lost and how much we recovered based on the percent yield. The percent yield tells us how much we actually recovered, and then we can subtract that from 100% to get the amount or percent that we lost. Or we could do this, and or and this step number 4 is not often done. Sometimes we'll do this. It depends. We can calculate the amount of leftover excess reagent. This is more commonly done for B, is more commonly done here. The calculation for the amount of leftover excess reagent we could see here. Like in the previous example with the bicycles, you could do this in your head. So if we have 3 frames and 4 wheels, we could build 2 bicycles, and then how many frames, the excess reagent, how many leftover frames do we have? Just 1. And so oftentimes we'll do that to determine how much leftover stuff there is. And so these are the steps that we typically take in a limiting reagent problem. Well, let's take a look at their example here, the limiting reagent problem. Calculate the mass of antimony 3 iodide, SbI3, that can be produced by the reaction. Antimony is a semi-metal there. With semi-metals, you can do different things. You can call this, for example, like an ionic compound, antimony 3 iodide, or you can call it like a molecular compound, antimony triiodide. Antimony +3 and +5 are the common charges for antimony. It's like nitrogen. That can be produced by the reaction of 129 grams of antimony. This is elemental antimony. And 381 grams of iodine. So iodine is elemental iodine, which would be I2. It's a diatomic element. And so what we're going to do is this. Whenever we're given the amounts of both reagents, let's go ahead and write the equation first, the reaction. And so this is going to be antimony, Sb, which is a solid, plus iodine. Iodine also is a solid. Bromine's a liquid. Chlorine and fluorine are gases. Iodine's a solid. It's going to produce SbI3. So how are we going to balance this? Well, I need 3 iodines here. 3 iodines will give me 3 halves iodine here. If I do 3 halves times 2 gives me 3. And then it's balanced. But with stoichiometry, I don't like working with fractions. And so I'm just going to double everything. So this will be 2, 3, 2. And so we're given A, which is antimony, and B, which is iodine. And so the first thing is I assume there's excess iodine and calculate how many grams of SbI3 I can produce based on A. That's calculation 1. Calculation 2, I would calculate how many grams of SbI3 I can produce from the iodine, assuming I have excess antimony. And then see which one yields a smaller amount. And so let's take a look at what they did. So the product here is SbI3, and we're going to look for the smaller amount of grams of SbI3. Is A going to give us the smaller grams, or is B going to give us the smaller grams? Okay, here again they give us the molar mass, which saves us some time. It's nice not having to calculate that. So we have 129 grams of antimony, A, and so how many grams of product can we form? So we just do a gram to mole, mole to mole, mole to gram conversion to get 532 grams of SbI3. So this is calculation 1. Then in calculation 2, we repeat the calculation except from B's perspective. Here we have 381 grams of iodine, which is B. How much product can we get? So this should be lowercase here. So we'll go grams of iodine to moles of iodine to moles of antimony triiodide or antimony 3 iodide to grams of SbI3. So how many grams did we start off with the iodine? 381. So we'll go 381 grams of B to moles, mole to mole, and then figure out. So iodine yields 503 grams of product versus antimony. Antimony yielded 532 grams of product. So we have 503 versus 532 grams of SbI3. And so we pick the smaller amount. The smaller amount is going to be 503. The smaller amount, therefore, antimony is the LR. How many grams of antimony did we have? 129 grams. So 129 grams of antimony is the LR because that produced the smaller amount. 381 grams of iodine is the excess reagent. And so the theoretical yield is 129 grams. Oh no, that's not the, sorry. What is the theoretical yield? The theoretical yield is the smaller amount, 503 grams. This is our theoretical yield. It's impossible to get 532 grams. It's impossible to get 532 grams because we'd run out of antimony before running out of iodine. And so what they say here is 129 grams of antimony is enough antimony to produce 532 grams. What are they saying here? But there's only enough iodine. Oh, this is the theoretical yield, sorry. The smaller amounts of theoretical yield. Let me back up here, because I got it mixed up. So forget what I just said. The 503 grams is our theoretical yield. That's a smaller amount, but the smaller amount was produced from the 381 grams of iodine. And so the 381 grams of iodine is our limiting reagent because that produced the smaller amount. Versus this is the 532 grams was produced from the antimony. And so the antimony is our excess reagent here. So 129 grams of antimony is enough antimony to produce 532 grams. But we can't produce 532 grams because we're going to run out of the limiting reagent, which is the 381 grams of iodine. But there's only enough iodine to produce 503 grams of antimony triiodide. So we're only going to produce 503 grams of antimony triiodide. All right, this last calculation that they're doing here is 4B. In this calculation, we do it in 2 steps. We know that 381 grams of iodine is our excess. And so amount of iodine that is excess left over equals the initial amount of iodine minus the amount of iodine consumed by the LR, the limiting reagent. So the amount of iodine initial is 381 grams. Out of that 381 grams, how much of that was consumed by the LR? And so the amount that's consumed by the LR, we get that from stoichiometry. We have to do one more stoichiometry calculation. So in other words, if we want to figure out how many frames are left over, let's say, in building our bicycles up here, what we do is we take the initial amount, 3 frames, minus the amount that was consumed by the limiting reagent. The amount consumed by the limiting reagent was 2 frames. And so 3 minus 2 gives us 1 frame left over. And so that's what we're going to do here, except we need to do it in grams, and therefore we have to do it using stoichiometry. And so what is the stoichiometry calculation? Well, for every antimony, we need 3 halves I2, or for every 2 antimonies, we need 3 I2s. And so that's our stoichiometric ratio there. And since we're doing it in grams, we'll have to do it like this. So they're doing it 381. I do it a little bit differently here. And so my calculation would go like this. I would calculate the amount, just say, or my calc, amount of iodine consumed by the LR. Oops, am I doing it backwards again? What was the LR?
Yeah, iodine.
The iodine was the LR?
Yeah.
And the antimony was the excess. Oops, I did it again. Sorry. The excess was antimony. And so I have to figure out how much antimony is left over because I'm still thinking B. And so we'll have to take the initial amount of antimony minus the amount of antimony consumed by the LR. And so the initial amount of antimony was how much? 129 grams. Okay, now we'll have to do the stoichiometry calculation here. So the amount of iodine, the amount of antimony consumed by the LR iodine is here. Actually, that's what they did. So this is the amount. So this is the LR here. And we're going to calculate how much iodine was consumed. So we'll go from grams of LR iodine to moles. And then moles of iodine to moles of antimony. This is the limiting reagent. Oh, excuse me, this is the limiting reagent here. This is the excess reagent. To grams of antimony. And so this is 122 grams of antimony consumed by the LR being 381 grams of iodine. And so we had 129 grams of antimony initially, and 122 grams of the antimony were used based on our stoichiometry calculation here. So this was given. This we calculated using stoichiometry, which means 7 grams of antimony left. And so the way they did it is the same way I would have done it here. I just keep mixing it up. But that's basically it. All right, any questions on limiting reagent? So the limiting reagent, this is a pretty standard problem, so you should be able to do all these steps here. All right, sometimes we're given the amounts of energy in a particular reaction. And energy, we can talk about in different units here. A common unit is a joule or kilojoule. Probably kilojoule is more common because joules is too small. But this is the definition of a joule here. It has a mechanical definition. And the mechanical definition is if you lift a kilogram 1 meter in the air against the force of gravity, then you've just spent 1 joule of energy. Whereas the calorie has a different definition. The calorie is, do you know, the definition here is 1 calorie is defined as the energy required to raise the temperature of 1 gram of water by 1 degree C. So if you had 1 gram of water and you increase the temperature by 1 degree C, so it's still 1 gram of water, but it's 1 degree C higher. So if we start off at 4 degrees C and go to 5 degrees C, that would be the definition of a calorie, basically. It turns out it costs more energy to warm up a gram of water than to lift 1 kilogram mass. And so 1 calorie is equivalent to 4.184 joules. In other words, there's 4.184 joules per calorie. This is they're saying this is exact. Usually this is just it's like 4.1845. I don't know why they're making this one exact. It goes on to more joules. So typically we take this conversion as 4 sig figs. Actually, let's take a look, because usually when I go to 4 sig figs, I go 4.185. Gram calorie. That's odd. Okay, so they changed it. The precise equivalence between calories and joules has varied over the years. But in thermochemistry and nutrition, it is now generally assumed that 1 calorie is equal to exactly 4.184 joules. It wasn't always like this. It's actually slightly different, but I think as a matter of convenience, they just changed it. This is the same thing with Avogadro's number. A whole bunch of things have been changed. So let me fix this. They're correct. I was wrong here. This should have been exactly. I'll just write it in faster. So that means this isn't 4 sig figs. How many sig figs is this? If it's exact, how many sig figs? Infinite. That would be infinite sig figs here. Let's see. So we have kilojoules and kilocalories when we have lots of energy. You know, oftentimes we don't have to heat 1 gram, we have to heat, 1,000 grams, like a liter of water. And therefore, it would be easier to talk in terms of kilojoules. We'd need 1 kilocalorie to heat 1,000 grams. Or we'd need 4.184 kilojoules to heat that. We actually have 2 types of calories. There's a calorie with a small c and a calorie with a large c. This is a chemical or science chemical calorie. This is a nutritional calorie. So let's say, how many calories is the Big Mac there across the street? 1,000? 1,200? 12,000? I don't know. A lot. But actually it's a million chemical calories, but it would get tiring. If you look at nutritional values on food, it would get tiring talking about millions. How many millions of calories did you consume today? And therefore what they did was they changed it. Now like 1,000 nutritional calories is 1,000,000 chemical calories. And so a food calorie is equivalent to 1,000 chemical calories. And so 1 food calorie with a capital C is equal to 1,000 chemical calories with a little c. We're not really going to do much with the food calorie. We're going to be talking about chemical calories, pretty much. There are a couple of homework problems with food calories in there, so be aware of that. So we can just do conversions. These are just converting 42.5 kilojoules into kilocalories, calories, and joules. The easiest would be to calculate calories. I don't like these conversion factors that he has here. What I would have done is I would have just done 42.5 kilojoules and then convert that to joules. There are 1,000 joules per kilojoule. And then convert that to calories. In 1 chemical calorie, there's 4.184 exactly joules. And then convert that to kilocalories. 1 kcal is equivalent to 1,000 cals. And so they did it in 1 step. I would have done it in 3 steps. And then we can convert it to others, calories and regular joules. This would be 42,500 regular joules, etc. So those are just inner conversions between those. There are other units too that you encounter sometimes. BTU, British Thermal Unit, etc. for energy. So we have thermochemical equations. Both energy and mass are conserved, we have the combined mass energy conservation law. So there could be heat given off. Energy is neither created nor destroyed. So if we go down in energy, let's say we go downhill. So let's say you're at the top of the slide and you go down to the bottom. There are different things that can happen. Where does all that energy go? All that energy could go into, depends on how steep this slide is. You might impact the bottom here hard. If you impact the bottom there hard, then that energy that you lost in the height here was transferred into what we call kinetic energy, the impact there. Or if you slide down this slowly, you can generate friction, and you can feel the heat, of your pants warming up, whatever. It's the friction. And so energy is neither created nor destroyed. So if a reaction loses energy, that energy goes somewhere. And typically that energy is given off as heat. Or if we go up, the energy has to come from something. And typically we have to input heat. Heat is just this exchange of energy, usually. Heat of reaction or enthalpy of reaction. Heat and enthalpy of reaction are kind of the same thing. And that's given a symbol. This is the enthalpy of reaction here. Delta, which is a change in energy. So there's some change in energy here. R stands for reaction and H stands for enthalpy. Given the symbol H. And so delta HR is the heat of reaction. Or enthalpy of reaction. Same thing. For us right now, but in Chem 1A, there's subtle difference. But oftentimes they're the same, regardless. So enthalpy is the heat content. Heat content it's not necessarily hot. It's just energy. Like if heat is given off here due to the friction of this person going down the slide here, did that person start off as being hot? No, the person was probably just at normal temperature. But when they slid down the slide, it generated heat. That heat came from not having heat content. Heat content, it could be hot. Like say if you have a hot pot of water, the hot pot of water is going to get cool as it releases heat into the room. And so the heat content here is a little different. It's the energy content here. It's not that the person started off hot and is giving off heat. And so this is why I put quotation marks here. It's the heat or the enthalpy content or the energy content of the chemical system. It's not necessarily that they're hot. It could be that they're hot, If they're hot, they're going to cool down. But it doesn't have to be. H is the symbol for enthalpy. Delta indicates a change. R stands for reaction. Exothermic means heat is given off. So in this case, it would be exo. Heat is given off. If heat is inputted in, that is, we have to input heat here, that's called endo. And so this would be exo. This would be endo. I think we talked about this before. So exothermic means we're losing heat. Enthalpy of the system goes down. Delta H has a negative value. So delta H is less than 0 usually. The negative just means that we're losing heat. In other words, it's negative. When we say less than 0, it just means it's a negative number. Negative number means losing heat. Endothermic is going to be positive. That is, delta H is going to be greater than 0, which is positive, and that means we're gaining heat or energy. That would be endothermic change. And so an example of an exothermic change where you have to lose heat would be like freezing water. If you want to freeze water, you have to remove heat. In this case, it would be just temperature, heat content. And so we'll just cool it down to remove the heat. If we want to melt ice, then we're going to have to add heat to melt the ice. And so here it's straightforward. If we want to be really accurate, then what we need to do is we need to make sure the atoms are balanced, that is, mass is balanced, and energy is balanced. In this case, this turns out to be higher potential energy going to lower potential energy. So we're losing potential energy. You know, a mixture of, this is called ethane, and oxygen is flammable. When you burn it, you form CO2 and water. CO2 and water is a lot more stable. Water is a liquid here, which they forgot, the L. But we're going from something that's highly flammable to something that's quite stable. And we're losing potential energy. Well, that potential energy has to go somewhere. And the potential energy is going to be lost. This is lost energy. We're losing this to the surroundings. And so we're going to lose 2,855 kilojoules for every 2 moles of ethane that are produced. Another way of showing this is it's a product. So this would be, let's say, minus $20. Over here, take a look at the sign. Note the sign is positive here. So this is what the reaction is giving to the surroundings. So when you burn the ethane and the oxygen, you're going to produce CO2 and water. And so you're giving CO2 and water to the earth here by burning the ethane. One thing people don't want is they don't want the CO2. A lot of people don't want the CO2 because they are saying that CO2 is responsible for what? Global warming. Yeah. And so it's releasing CO2 and water into what we call the surroundings. But it's also losing energy, and so where does that energy go? It also goes into the surroundings. So we're also going to get 2,855 kilojoules. And so if we lose, let's say, $20, then where did that $20 go? It went somewhere, right? Because can the $20 just vanish? Oh, I suppose it could if you burn it or something, and it'll form CO2. But no, the $20 is still there. You just lost it. Where did it go? It went to the surroundings. And so if the $20 went into the surroundings, did somebody just gain minus $20? No, somebody gained a $20 bill. And so like money, energy is always positive. The negative sign that we attribute to this is just to tell us that we lost it. A positive sign means we gained it. But energy, like money, is always positive. And so we can't, there's no such thing as negative. You know, if you could make, let's say you made a candy bar, and this candy bar had negative 2,000 kilojoules, then that would be great because you'd have something for diets or something. You know, it'd be easy to diet. You just eat a bunch of those candy bars and you start losing energy, right? But it's not the case. Oops. Unfortunately, energy is always positive. And so we have 2 ways of representing the energy in this case. This is exothermic. In this exothermic reaction, one way is we say that delta H, the enthalpy of reaction, is negative 2855. This tells me it's exothermic because we must have lost it. The second way is to write it as a product. So now this is balanced. The total energy here is equal to the total energy here. And the energy is balanced. Well, what is the total energy here? The total energy here is the sum of the kinetic and the potential energy. But the only thing we're looking at is, in this case, is the kinetic energy stays the same, so there's a difference in potential energy. So the difference in potential energy here is this. The potential energy of this is equal to the potential energy of this plus this. That is, this is 2,855 kilojoules less in potential energy than this. And so if we're looking at this, we often write a potential energy diagram. A potential energy diagram would be shown like this. Oops. Just highlight it here. That is methane, or not methane, this is ethane, C2H6, 2 ethanes plus 7 O2s. I'm going to get rid of the states because there's not enough room here. Is 2,855 kilojoules higher in energy, potential energy, than 4 CO2s and 6 waters. So here we'll have 4 CO2s plus 6 waters. Water I'm going to write as liquid because it makes a difference if the water is a gas versus if it's a liquid. And the drop here is minus 2,855 kilojoules. Or if I were to reverse this and go up, let's say I reverse the reaction, then I'd have to input plus 2,855 kilojoules. So the drop is 2,855, and the climb up is 2,855. And so this would be a potential energy diagram here, showing the difference. The higher we go, the higher the energy. The lower we go, the lower the energy. And so energy increases as we go up. Here. So here's an endothermic reaction. I can tell because of the positive, it's endothermic. And so that means I have to input it. In terms of potential energy diagram, that means nitrogen and hydrogen are a higher potential energy. So nitrogen plus 3 hydrogens is going to be at a higher energy than 2 ammonias. And in order to go from 2 ammonias to nitrogen and 3 hydrogens, we'd have to input plus 92 kilojoules for every 2 moles of ammonia we have. All these are gases. So we can do stoichiometry with this because we just treat this as another product or another reactant. In this case, it's a reactant. In this case, it's a product. So the thermal decomposition of limestone, calcium carbonate, to lime, solid calcium oxide, and gaseous carbon dioxide is an endothermic reaction requiring 178 kilojoules per mole of calcium carbonate. And so if we have 1 mole of calcium carbonate, it can decompose. This is what we call Lewis acid-base decomposition. This is not a redox decomposition. And so here, that means that calcium carbonate is more stable than the products here, and so we're going up. And we're going to go up by 178 kilojoules. This is going to require energy to accomplish this. This endothermic reaction is one of the, I think it was, one of the top was this one. 10 chemical reactions that changed the world. Ammonia synthesis, which is, we looked at the decomposition of ammonia, but the reverse process is for sure one. Polyethylene, combustion of hydrogen, reduction of zinc and silver, synthesis of urea, PCR, fat hydration. This is ozone destruction. Water with carbon dioxide, saponification. That's interesting. They didn't classify. It depends on who did this. Some people put this in the top 10. Some people put it in the top 5 reactions. Oops. Six chemical reactions that changed history. And chemical. This is one of the ones that changed the world. And so there are a lot of people who list this as one of the top 10 chemical reactions. Why is that? Why that is because calcium oxide. Calcium oxide was a critical ingredient to concrete. And so the Romans built these kilns to make this stuff. They call it lime. And so lime was critical for concrete, and that's just calcium oxide. And so they had these kilns. They needed coal, though, to reach these high temperatures that are required for this. And so you can't just burn wood. Wood wasn't going to get hot enough. And so fortunately they had coal. They could produce lime, and from the lime they could make cement, which was critical for concrete. Those structures are still standing. A lot of those structures are still standing today. Another top 10 reaction was this one here, the reverse of this one. The reverse of this one's extremely difficult. Even though you think the reverse is downhill, doesn't it look downhill? The reverse reaction looks so simple. We're just going to lose 92 kilojoules. And so if we react nitrogen with hydrogen, it should be a simple reaction to produce ammonia. But it turned out it wasn't, because it doesn't go straight downhill. When we look at it, there's an uphill part before you can go downhill. The uphill part is we have to break the bonds. Breaking the bonds in nitrogen is extremely difficult because nitrogen has something that's called a triple bond. And triple bond is very, very stable. And therefore, we have to break that triple bond or close to it in order to get this to react. And it turns out it's not so easy. In fact, nitrogen, they call it a pseudo-inert gas or pseudo-noble gas. It's so unreactive. So, air consists of about how many percent nitrogen in air? About 80% nitrogen, but it's totally unreactive. The nitrogen in air pretty much only reacts with certain legumes, so these beans. But it's a pseudo-noble gas, and so it's not straight downhill shot like this. It's a little bit more complicated. But this was a huge reaction, the reverse of this, because what they use. Do you know what they use ammonia for? This may be the number one reaction here. They use it as fertilizer, and so this, I think they credit this reaction for. For ending starvation in at least around that time period. As the food output, the crop yields increased dramatically. after that. So what we're going to do is we're going to treat this as just another reactant in this case. So this would be A plus B, or we treat this as another product. Like C plus D plus E. That would be the product. So we can treat it as a reactant or product. And so we can do thermochemical stoichiometry by adding a couple of branches here. So if we know how many kilojoules per mole, then we can figure out how much energy is produced. Or we can figure out how much energy is consumed in particular reactions here. And so we can just add these as additional branches to our stoichiometry here. So what mass of liquid N octane, N stands for normal octane, a component of the gasoline must be burned to provide 9.05 times 10 to the fourth kilojoules of heat. And then they give us our enthalpy of reaction. The enthalpy of reaction is minus, which means we're going to lose 5,471 kilojoules for every mole of octane that's burned. So we can just use dimensional analysis for this. Here we'll just start off with our given and then try to get rid of kilojoules. Well, the kilojoules we can get rid of are this here. For every 5,471 kilojoules released. Note, they had a negative sign here. They don't put a negative sign here in this case. And so what we say is that we need this amount released. And so there's two ways of doing this particular problem. They want 9.05 kilojoules of heat. And so the two ways is we could just say it's 9.05 times 10 to the fourth kilojoules lost, that is positive, or we could say we want negative 9.05 times 10 to the fourth kilojoules. This negative means it's lost. And so if we put the negative here, then we'd use the negative here because the negative means it's lost. Or we get rid of the negative and just say this is the amount lost or released. And this would be the amount released for every mole. We have to make sure we're consistent with the sign convention. So we must be consistent with sign convention either way. Let's say you need 1,000 calories. And so, and you calculate the number of grams of candy bar you have to eat to get 1,000 calories. So, and then your calculation came out, you need a negative 100 grams of candy bar. Can you eat negative 100 grams of candy bar? Does that make any sense? No, but people do these calculations and they come out with negative 1,893 grams. What does that mean? Negative 1,893 grams of gasoline. Can you get that? Can you buy that? No, so you have to watch out. You don't want nonsensical numbers here. And so, in other words, they got 1,890 grams of octane based on this. So they did the kilojoules to moles, moles to grams conversion here. That's assuming we have plenty of oxygen, which we can do. We always assume, if it's not specified, we always assume that there's excess other reagent. If it's not specified. If the amounts of two reagents are given, then we have to do a limiting reagent problem. If only one reactant is given, then we assume everything else is in excess. So when we burn octane, we need oxygen. What happened to the oxygen? They don't tell us how much oxygen there was. Well, it doesn't matter. We're going to assume we have enough oxygen to completely combust all this all this octane here. All right, I'm going to stop here. We'll take a break, then start up again. Yes. The negative's given, so you have to figure out how you're going to deal with it in the problem. We could leave it as negative. If we leave this, so for example, if we leave this one as negative, then we have to change this to negative because that's the amount we need to lose. if we change this to positive, then we just leave that as positive. So do you see there's an inconsistent sign there that we have to make sure it matches? As negative, yes. If it's exothermic, it's usually given as negative, and then we convert it to positive when we do the calculation. But it depends on which reaction we're looking at. Sometimes we don't. Sometimes we'll just leave it as negative. In stoichiometry, we'll typically change it to positive.
So exothermic is given as negative and endothermic is given as positive?
Yes.
But usually in these types of problems, like whether it's negative or positive, it's stable.
So I need to start chapter 11. Chapter 11 is kind of long. To get back on track here. So we'll come back to stoichiometry. I'll probably do a problem in class related to stoichiometry, but I want to start talking about quantum. We talk about atomic theory. Atoms are made up of protons, neutrons, and electrons. Using atomic theory, is it easy to predict the properties of atoms? So if we look at hydrogen, the simplest atom, versus helium, the second simplest atom, could you predict it? So in other words, hydrogen has how many protons? One's correct. That's good. How many does helium have? 2. 1 and 2. And so can you account for the huge differences in properties? Hydrogen's quite flammable. Is helium flammable? No. Helium you can't burn. It's not flammable. And so actually it's not enough. What we need a more detailed model of the atom. And the more detailed atomic model is going to come from quantum theory, quantum mechanics, quantum general. That's what's going to give us a detailed picture of the atom. And so when we think of theories, where do theories come from?
Observation.
Usually they come from observations. But they could also come, like, for example, could you hypothesize the theory of the elements to account for the property differences between hydrogen and helium? Helium you can't burn, hydrogen you can burn. Hydrogen likes to form a diatomic. Why don't helium like to form diatomic? It would be unstable if it did form a diatomic. It's so unstable it doesn't exist. So you don't have diatomic helium because they don't like to pair up. But can you think of a theory to explain that? Or hypothesis? I mean, people will try, but it's pretty hard, right? Do you know where quantum theory came from? Quantum theory took a really the development of quantum theory took a path you wouldn't expect, and it's one of these paths that takes you down this road, and eventually you get to some place that you wouldn't have expected to have been, let's say. And so what were the observations? We'll talk about the observations that led to quantum theory, but in order to talk about the observations, we have to talk about some light. Because the observations that led to quantum theory were these unusual light patterns that were observed. And so the basic rundown was these unusual light patterns led to certain laws, like the Rydberg law or the Rydberg equation, which led to after what does it go? It goes observation patterns to what? To law to hypotheses. And we came up with Bohr hypotheses. But eventually it leads to a theory. And the original theory that it led to was called the Bohr theory, but the Bohr theory turned out to be incorrect. And eventually it was modified to make quantum theory. But let's start off with the observations first and then see the path that we take from the observations to the theory. And so this is the development of quantum theory. The development of quantum theory started off with electromagnetic radiation. Electromagnetic radiation is light. But it's not just the light you can see. There's a whole bunch of light that you can't see. And there's a little bit of light that we can see. Actually, when we look at electromagnetic radiation, there's lots of different types of electromagnetic radiation. The part that we can see is called the visible part of electromagnetic radiation, or the visible spectrum. And the visible spectrum just makes a tiny fraction of the total light that's possible. And some things we don't really think of light. For example, FM radio waves. Do you think of those as being light? No, because we can't see it. But it's invisible, but it behaves just like the visible light that we can see. And there's just a subtle difference between that. And so this is light as well. Microwaves, that's light. Infrared radiation, that's light. Ultraviolet radiation, that's light. X-rays are light. Gamma rays are light. How about sound waves? Are sound waves light? It turns out sound waves aren't light. Sound behaves differently. And sound waves are not considered light. And electromagnetic radiation is considered light. And so let's take a look at electromagnetic radiation in more detail. Most of the electromagnetic radiation is invisible. We can't see it, but even though you can't see it, you can have detectors that can observe it. And so energy in the form of electric and magnetic waves, including gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. Energy is transmitted. Okay, so this is energy. Light is energy. First thing, light is energy, and it's energy that's transmitted at the speed of light. See, the speed of light is fixed at 3.00 or 2.998 times 10 to the 8 meters per second. If we want 4 sig figs, I don't think they changed this to exact 4 sig figs. Or to 3 sig figs, it's a lot easier. 3.00. Or 186,000 miles per hour. So light moves at the speed of light. This is in a vacuum. light travels slower through matter, like water or whatnot. All right. And so it talks about electric and magnetic waves. And we have these wave properties that can be described. Like when we look at a wave, okay, the first thing is we'll see this. Light is a wave of energy or packet of energy that's traveling extremely fast. How fast is it? It's traveling c. C is the symbol that we give to the speed of light. So it's moving extremely fast. When we look at waves, there are certain features of the waves. And so this is electric part of the wave. And so if we look at the electrical component of the wave, this is the electro part of electromagnetic spectrum. Then what we see is we see a wave like this. A wave, normally if we think of an ocean wave, there's amplitude here. This would be positive amplitude. Say this would be negative amplitude here. Amplitude is just how high it is. In terms of electro part, this would be positive, so the wave is positive in one instant of time, in the next instant it's negative, and then it goes positive, negative, positive. So what we see is we see something called an oscillating electric field. An oscillating electric field is this. Imagine this wave is traveling at us. If this wave is traveling at us, what we see is a positive, and then in the next instant it goes to negative, and then it goes positive. And so what we see is this positive, negative, and it's oscillating like this, between positive and negative. And how fast is that moving? Well, that's moving at the speed of light, 186,000 miles an hour, so these oscillations are very fast. These oscillations are going to depend on, how far the distance is, So we start off here, positive, and then we dip, and then we go back to positive. That's called one wavelength. And so it depends on that distance here, which we'll call lambda. And so the lambda is the peak to peak or the valley to valley distance. This would be lambda. Lambda has the symbol, this is the Greek symbol, this. And so this is lambda, Lambda, lambda. And lambda is what we call the wavelength, the peak to peak or the valley to valley distance. Lambda is usually in meters. And the speed of light is in meters. The speed of light, we'll just do the 3 sig figs, 3.00 times 10 to the 8 meters per second. And so that is 300 million meters per second. And so in 1 second, 300 million meters of it passes by. Lambda is going to be the wavelength in meters. And so the lambdas vary. When we look at the lambda here, wavelength in meters, we could have wavelengths on the order of 100 million, longer wave, to 10 to the minus 16. 10 to the minus 16 meters would be extremely small. Tenth of a, what is it? Extremely small. And so it depends on the wavelength. If you have about 300 million meters pass you in 1 second, and let's say it was 100 million meters, then we'd have 3 wavelengths pass by in a second. And so in a second, it would go like this. 3 wavelengths would be, you start up here, that would be 1 wavelength, 1 oscillation. The second wavelength, 2 oscillations. And the third wavelength, 3 oscillations. So that would be 3 up and down oscillations in 1 second. And we call that 3 cycles per second. 3 up and down cycles per second. And 1 cycle per second is called a hertz. So 3 cycles per second would be 3 hertz. So that would be 3 hertz oscillation. If our wavelength were 300 million meters, 300 million meters would be required to go from one peak to the next peak. And our speed is 300 million meters per second, then we just have 1 hertz. That is 1 oscillation in a second. But the wavelengths can vary dramatically. So if the wavelength were smaller, let's say, AM radio has wavelengths on the order of 10 squared, 100 to about 1,000 meters. So 100 meters would be the distance from one peak to the next peak to 1,000 meters. And what we get there is AM. Do you know what the frequency of AM is, roughly? Usually on the kilohertz, right? 900 kilohertz, 1,000 kilohertz on the AM. I don't know if anybody listens to AM radio, but if you do, you're dialing to the kilohertz. Do you listen to FM radio? FM radio would be a shorter wavelength. Shorter wavelength means more cycles per second, and so FM radio would be megahertz, usually, like 100 megahertz, 200 megahertz, something like that. 89 megahertz. Microwaves are gigahertz. And so usually your microwave oven operates like at 4.8 gigahertz, something like that. And you have centimeter long wavelengths in microwaves. And then we can go on. After giga, we typically don't talk about that. We usually talk about wavelength. Infrared has wavelengths of about 1,000 nanometers plus. Nanometers 10 to the minus 9 meters, something. No, 10 to the 7. No, yeah, 10 to the minus 9. 10 to the minus 9 meters. Ultraviolet, X-rays, gamma rays. Gamma rays have extremely short wavelengths and extremely high frequencies. Look at gamma radiation can have 10 to the 24, 10 to the 22nd cycles per second or hertz. Here. So when we're looking at the distances here, the wavelengths of X-rays are about the same size as what? Atoms. About the same size as atoms. So what we're looking for is how matter and light interact. So if we think of an ocean wave, it depends on how light and matter interact. So for example, if you have a small boat versus a big boat. Let's say if you have a small boat, is this small boat going to interact with the waves much? Yeah, the small boat is going to be heavily influenced by these waves because it would just go up and down. Like that. Versus, let's say you had a big boat. Is this big boat going to be influenced much by these small ripples? No. So, one thing is this. Actually, let me not talk much about that. I think what we'll do, instead of talking about this, I think what I'm going to do is talk about this. So it turns out that what do we want to know about light? Well, we'd like to know certain things. We want to know the wavelength, lambda. We know the speed of light, which is just a constant. This is a constant in a vacuum, 3.00 times 10 to the 8 meters per second is a constant in a vacuum. A vacuum means there's no matter there that can slow light down. But in water or other matter, in air, it slows down a little bit. And then we want to know the frequency. The frequency is nu. And this is in cycles per second, which is called a hertz. Hertz is abbreviated HZ for hertz. And then the last thing we want to know is the energy of the light. There are two types of energy that we look at. The energy of the light is going to equal h, which is also a constant. This is called Planck's constant. Times nu, the frequency. Or it's equal to h times c over lambda, because the relationship between c and nu is given by this equation. That is, c is equal to nu times lambda. The speed of light is equal to the frequency times the wavelength. And so what this says is that the higher the frequency, the higher the energy. The lower the frequency, the lower the energy, the light. So gamma rays have very high frequencies, so very high energy light, whereas visible light has lower frequencies, therefore lower energies. It's inversely proportional to wavelength. That is, as the wavelength decreases, frequency increases. As frequency increases, the energy increases. And so long wavelength light has lower energies. Short wavelength light has higher energies. So these are the basic relationships. So here, the highest energy light is gamma rays. Gamma rays have the highest frequency. You can see the numbers here, and the shortest wavelengths. The lowest energy light is the long radio waves here. The long radio waves have lower frequency and longer wavelength. Then we have a whole range of frequencies and wavelengths here. And so what we're going to do is we're going to break this down in terms of energy. What's the highest energy light?
Gamma rays.
Gamma rays. So we're going to put that at the top. in terms of the energy of the light. Gamma has this symbol. This is symbol for gamma. And that's going to have the highest energy light, which is going to be the shortest wavelength, highest frequency. So high frequency, short lambda. So high nu, short lambda. High frequency, short wavelength. Which gives us high energy. Now, I told you light comes in these little wave packets. And a packet of light is called a photon. So, one way of thinking about this is a photon is like a particle of light. But the problem with a photon is it doesn't have a rest mass. You can't weigh a photon. And so it's not a particle in the sense that an electron is a particle. Electron does have mass. You can weigh it. A photon doesn't. It's just energy. But energy and mass are related from Einstein's equation, E equals mc squared. But anyway, we have this packet of light. And so this is a high energy packet of light. And so what do gamma ray photons do? Gamma ray photons cause damage. Because what happens is this. If you're looking at a gamma ray photon, gamma ray photons have very high frequency. Very high frequency means it's oscillating plus minus very fast. So let's say you're an electron. The nucleus is kind of massive. So if the nucleus gets hit by a photon, it's got a lot of mass. And mass means inertia. Electrons are really light. They're about 2,000 times lighter than a proton. And so electrons are a lot easier to manipulate. So let's say you're an electron and you get hit by a gamma ray photon. So what charge is an electron? Negative. And so what's going to happen is it's going to be attracted to positive, repelled by negative. So as this field passes, what happens is the electron starts to oscillate. And if it's a gamma ray, what happens is the electron starts to oscillate extremely fast. So fast that the electron gets knocked off the atom. If the electron gets knocked off the atom, do you know what we call that? We call that ionization. And therefore, we're going to form ions. And therefore, what we have is gamma rays are called ionizing radiation. They ionize most matter because they'll knock electrons off most matter. That's not good, usually. Sometimes it's good to form ions, but a lot of times we don't want to form ions. And so we call this ionizing radiation. In other words, it ionizes most matter. And oftentimes, do you want to ionize your DNA? No, you don't want to ionize your DNA. It's going to cause...
Would you die if you did?
It's not like you'll die instantly, but what happens is it could cause defects, mutations, which could eventually lead to cancer, which could eventually lead to death. But gamma radiation, you could die because if you ionize enough of the matter, things aren't going to function as normal. And so there's radiation sickness, which would cause death, faster than cancer. In fact, did you hear about there was, this happened at, apparently it's very excruciating death. And somebody survived it. Have you heard of this person? I think there was a polonium. I thought that it happened at LAX. Was polonium the gamma ray emitter? Either alpha or gamma. But there are 2 people who were poisoned at LAX. I'd have to look it up again. But they were given a radioactive isotope, which emitted constant radiation. But the problem is how do you get rid of the radioactive isotope once you've consumed it? And so there's not much they could do for them, unfortunately. So anyway, gamma ray. X-rays are also quite energetic, but not as energetic as gamma rays. So X-rays are a little less energy. And so they aren't going to ionize as much matter, but they'll cause damage. Oops. X-rays. A little lower in energy, but still high energy. And we call gamma rays and X-rays ionizing radiation. A little lower energy than X-rays is ultraviolet. Ultraviolet can ionize some things, but not a lot. And so typically what ultraviolet does is it breaks bonds. What holds the atoms together in a bond are the electrons. And so if you excite it enough, let's say you have electrons in a bond and you excite those with ultraviolet, and eventually they split apart. There's a pair of electrons that form a bond. It splits apart and breaks that bond in DNA. So ultraviolet causes bond breakage, not necessarily ionizing radiation, but very damaging nonetheless. Ultraviolet. And then a little lower in energy than ultraviolet, we have violet light. Violet typically doesn't break bonds. It could, some people are saying you need, have you heard of blue blocker glasses? A lot of people they want blue blockers because they are worried about eye damage caused by violet light. Not necessarily ultraviolet, because hopefully your computer screen isn't spitting out a lot of ultraviolet light. If your computer screen were spitting out a lot of ultraviolet light, then you'd worry, but there is some violet light, from there. And so they want to block that out because the violet, although not as damaging as ultraviolet, can still cause some damage. Not just violet, but people are worried about indigo too. Indigo is a little less energetic, and blue. And so these people are worried, these blue blockers, they want to block out the blue, indigo, and violet, and of course the ultraviolet, to prevent damage. Potential damage. Then they don't worry too much about yellow or orange or red. Red is the lowest energy. In the old days when they had photographic films, they used red light bulbs. They used red light bulbs because they didn't want to expose the film necessarily. The film is light sensitive. And so the weakest form of visible light is red. And so if you have a red room, then, you don't have to worry about,
I just have to ask because it's the only color that I've been. Is there green light? Or
Oh,
is it,
no, there is green. Shoot. That's because I missed it.
okay.
Green comes between yellow and blue. Sorry. So, yeah. Red is the weakest of the visible. Violet is the strongest, and these are the colors of the rainbow. And so this is what we call visible light. All the colors of the rainbow are visible, but not all the colors have the same energy. And so there's high energy visible light, which would be violet, and low energy visible light, which would be red. And so violet is going to have the shortest lambda of the visible and the highest frequency of the visible. And red light will have the longest lambda and the highest, not the highest, the lowest frequency of the visible. We spend a lot of time with the visible spectrum because this is what we can see with our eyes. And the way to remember this is, do people know the way to remember the colors of the rainbow? A lot of people do this. They remember Roy, R-O-Y, and then G, I forgot the G, and then Biv, Roy G. Biv. Have you heard of Roy G. Biv? Yeah. So Roy G. Biv is his name, or her name. That would be it. Or their name. So Roy G. Biv is one easy way, and we're just going from low energy to high energy. In visible light, typically doesn't break bonds. What visible light does is it excites electrons. So, you have electrons in matter, and electrons are going to get excited. They'll start oscillating, but they won't oscillate so much that they break apart from each other, and they won't oscillate enough where they ionize from the atom, or become ionized from the atom. And so that would be Roy G. Biv there. And what we say here is it excites electrons in matter. Electrons in matter. Some matter absorbs all colors of light. If matter absorbs all colors, then what color is it? We have black objects, and these objects absorb all the colors. Have you heard of these? What do they call them? Ultra black materials. Yeah, they're trying to make a black, the blackest of the black. It's weird. If you take a look at the YouTube video of something that has ultra black paint on it, it's hard to see. So this is an object painted with ultra black paint. It's the same object. Is that weird or what? It looks like somebody just blacked it out, Photoshop or something, but it's the actual object that's been painted with ultra black paint. There's a video of this too where they rotate it so you can see it. But it's weird. They're also trying to make an ultra white paint. Have you heard of that? If black absorbs all colors, then what does white do? Yeah, it'll reflect all colors. They want it to reflect all visible. Like, so for example, they're thinking of painting the roofs of cars with ultra white paint. And the reason for doing that is so that it keeps the interior cooler. Because you know what's lower in energy than red? What's lower in energy than red is infrared. And so they want these ultra white cars to reflect it, because this is why they're worried about CO2, is because it traps in heat. Well, cars also trap in heat. This is the greenhouse effect. And so they want to prevent light from getting in to heat up the car. And so let's see if I have the ultra white. This is ultra black. There's ultra white. These are already commercially available. This is really pretty recent. Scientists have developed the whitest white paint ever made. So reflective it can cool surfaces. So if you live out in the desert, if you live in LA in the summer, you want something to keep the car cool. I guess this is at Purdue. Holds up his lab sample of the whitest paint on record. It reflects 95.5% of the sunlight. Since then, they've made it even whiter, 98.1%. So this is in the Guinness Book of World Records. And so there's great application in this. You know, if you... So here they're taking some measurements, it looks like, the cooling performance. So if you put buildings, like out, like in Arizona or out in the desert with this, then you can save a lot of money on energy costs. In AC, air conditioning. Ooh, the air conditioning needs of a building coated with barium sulfate paint. So the barium sulfate is that white precipitate that's super white, are expected to decrease by 40%. That sounds ridiculous. Air conditioning needs of a building coated with barium sulfate paint are expected to decrease by up to 40%. That's simple. Barium sulfate's easy to make. Just use a double replacement reaction for that. Ooh, in 2019, a study in the journal Joule. What do you think Joule's main focus is? If they name a journal Joule, then you got to know the main focus of this journal has got to be what? Yeah, Joule is the name of the person, but what is he known for?
Calories?
Not calories, because Joule is a different unit. Calories came, I think, later than joules, maybe. I don't know. What came first, the calorie or the joule? Actually, I don't know. But Joule, it's got to be energy. So this is the kind of, people are worried about global warming. People are worried about global warming. A study in the journal Joule found to stop global temperatures from rising, you would need to cover 1 to 2% of the Earth's surface with reflective material like the whitest white paint. So if we just paint over half the area of the Sahara Desert with this barium sulfate paint, then maybe we can stop global warming, huh? Different ideas. Ooh, the world's widest paint previously required 0.4 millimeters. This is what I remember reading. It used to have to be pretty thick, but now they can just work with 0.15 millimeters or 150 microns. Yeah, so this came out in Chemical and Engineering News last year. So, what infrared does is it just causes what we call bonds to vibrate. And vibration, this leads to kinetic energy and heat. So infrared is often thought of in terms of heat. It's often thought of in terms of heat because causes vibrations to occur. And so it doesn't excite electrons, it excites vibrations of the atoms. Because the atoms are held together by electrons, and these electrons are going to vibrate or oscillate through the field. That's infrared. Lower in energy than infrared is microwave radiation. It's kind of weird because you would think a microwave would be higher in energy, but microwaves are actually lower in energy than heat lamps in terms of the photon energy. Now microwaves, they don't have enough energy to cause vibrations. What microwaves can do is they cause rotations of small molecules, like water. And so infrared will get vibrations, microwave will get rotations of small molecules. Like water. Then we have radio waves. Radio waves, they can't do much except maybe excite electrons in metals. The electrons in metals are very loosely held. And so you could get the electrons in metals to oscillate with radio waves. But if you put a metal in a microwave, what would happen? Have you ever tried putting a metal in a microwave? Yeah, you get sparks. And so microwaves can ionize metals. We'll just put that over here. Because metals have very loosely held electrons. Whereas most matter has very tightly held electrons, and we use gamma rays or X-rays to ionize them. But for metals lose their electrons quite easily. They're easy to oxidize. Microwaves are enough to do that. Visible light can too. You know, this is the whole thing with photodetectors, like photocells. In the old days, they'd have a light beam, and that light beam, once it's broken, triggers a signal beam. So if you break the path of light, in those they use visible light to ionize metals, which you can do, like lithium or some other metals. So the thing about white light is we're going to look at these two in more detail, black and white. So let me talk about that here. Have you ever heard of a black body? What do you think a black body does? black body absorbs all colors of light, right? And so, in other words, what does visible light do?
If it was the word.
Visible light excites electrons. And so you could excite the electrons a little bit, or you could excite the electrons a lot. So we could put infrared energy, and a black body should absorb that infrared energy. Or we could put it visible. And so what I'm showing here is the electron gets excited. As it gets excited, it goes up in energy. Eventually, we'll get to ultraviolet. And so not only does a black body absorb all colors of visible light, it should absorb all light. Infrared, visible, ultraviolet. Now, what can happen is, this is called absorption. If we reverse this and we excite a black body, what could happen is we'll have emission of light. So if we excite these electrons to all these energies corresponding to infrared, visible, and ultraviolet, then what we'll have is an emitter. Okay, this is not just reflection of light. What I'm going to talk about here is this. What we do is, if you take a black body and you heat it up, it'll start emitting light. And so what that means is we have these electrons, and the electrons are all excited throughout here due to the heat, the energy. And what happens is the electrons don't stay excited forever. Eventually those electrons will fall back down. So we don't call it a white body. What we call it is a black body emitter. Something like that. And so what we should see is we should see all the colors of the rainbow being emitted, because what happens is energy is neither created nor destroyed. And so if something's excited in the UV, then we should expect to see UV light emission. Visible emission. Infrared emission of light. And so what we end up with is we end up with something called an absorption spectrum. So if I look at the absorption spectrum from infrared through visible, we have our Roy G. Bibb, to ultraviolet. What we look at here is what intensity of light is absorbed. That is, how much of the light is absorbed, and we see a continuum. This is what we call a continuum. All the light is absorbed. So this is a continuum or continuous spectrum. As for absorbance, if we were to take that black body and excite it, so it starts emitting light, then rather than looking at the absorption of light, we're going to look at the emission of light in terms of intensity. So the emission of light, it would look like this. It would be a continuous spectrum of emitted light. You don't want much UV, so don't excite it too much. What we want is we want visible. We don't even want IR, but you're going to get IR. Have you ever felt a light bulb, how hot it gets?
Yeah.
That's infrared. You can feel the heat, but you can't see it. If we emit all colors of light, do you know what color the light is going to appear? What color light we emit? Actually, it is something. It's white light, you call it. White light. White light consists of all the colors of the rainbow. So let's take a typical black body. A typical black body would be like a metal, although metal doesn't look black in color. Let me see if I could do this here as a demo. It's a simple demo. So. It shouldn't be difficult. All right, so if I heat this, metal is typically thought of as good black body. Because metal, I'm going to heat this metal, although this is stainless steel. Unfortunately, I'm going to oxidize a little bit of it, but it's all right. This is just, I'll oxidize the bad end here. All right, so I'm heating it up, and I'm heating up the electrons in the metal. When I heat up the electrons, can you see it glowing? Well, it's not really glowing, but I can feel it. I can feel the heat radiating off this. And you know what that heat is? It's infrared light. And so I'll heat up the electrons here, and then this is going to emit infrared. And infrared I can't see, but I can feel. I'm not going to touch it because it's extremely hot, but I can feel the heat coming off this as infrared. Have you ever done this? Have you ever stood in the shade and put your hand out in the sun? Do you feel the temperature difference? Mm-hmm. It's not the air, because the air, is the air different between this and this? No, it's the same air. You're breathing it. What's different is your hand is being hit by the light, the infrared light, the photons. You can't see it, but you certainly can feel it. So it's the same thing here. Feel that. But what happens if I continue to heat it? Do you start seeing it? Can you see it glow? Yeah. It's glowing how hot? It's glowing red hot. And then eventually it's going to glow orange hot and eventually it's going to glow white hot. When it's glowing white hot, what colors of the rainbow is it emitting? All colors of the rainbow. And so this is how light bulbs work. The old light bulbs, they had a piece of tungsten. Why tungsten? Because tungsten has extremely high melting point. So they used a piece of tungsten and then heated it up. But they didn't heat it up with a flame. Do you know how they heated up the tungsten? By putting electric current through it. And so in an incandescent light bulb, you have a tungsten filament. And all you do is get it white hot. When you get white hot, then you get all the colors of the rainbow and you have a white light bulb.
How long would it take for that to determine the white hot?
It'd take a while. Take a little bit longer. But eventually I'll get this white hot.
Can you do it?
I don't know. It might start to melt. This. How long does it take? In the flame, it takes a long time because this just doesn't get hot enough to get it white hot. But Other things are a little bit easier. It depends on how big. You have a smaller point, you got to worry about melting, and then you could see. There's just too much spatula there. So anyway, we could try here to get this glowing white hot at the end without melting it, but this is contaminated. You see that yellow color of the flame? It's kind of contaminated with something. But the problem is oxidation. Do you see how discolored my spatula is now?
Yeah.
And that's going to decrease because it's creating an oxide, and it's no longer metal. It's a metal oxide. Metal oxides aren't going to behave the same because the metal oxide is going to have much tighter, more tightly held electrons. And so to prevent oxidation of tungsten in light bulbs, they use an inert atmosphere. And so the light bulb is encased in the glass, and inside that glass is no oxygen. You don't want any oxygen inside that glass, otherwise the metal's going to oxidize. So we should be able to make light bulbs out of anything. We should be able to make light bulbs out of metal. Because metal, you could excite the electrons a little bit, infrared, excite it more, red, excite a lot, violet. Excite it too much, we'll get ultraviolet. But we don't want to excite it too much because we don't want much ultraviolet light coming off there. So one of the things that people wanted to do is to make light bulbs out of different materials. So there's a light bulb over here, probably tungsten, making white light. And what we could do is we could separate the white light into the components. White light is all the colors of the rainbow, Roy G. did. And one way to see all the colors of the rainbow is to have like a prism like this, or diffraction grating, or like rain droplets. Rain droplets kind of act like a prism like this. Because light travels through water at different speeds, and it depends on the wavelength. And the prism is just glass here, and the light travels at different speeds in the glass depending on the wavelength. So some wavelengths a little faster, some wavelengths a little slower. And so anyway, we can separate out the colors of the rainbow using a prism or water droplets or something called a diffraction grating into its component colors: red, orange, yellow, green, blue, indigo, violet. Roy G. did. Yeah. In terms of increasing wavelength, decreasing energy, increasing frequency or decreasing frequency, and vice versa. And so this is the spectrum that we get from white light. And this is called a continuous spectrum because do you see any colors of the rainbow missing? No, it's just a continuum all the way from red. We have different shades of red all the way to violet. Different shades of violet, but nothing's missing. This is a continuum. So we should be able to make a light bulb out of anything that has electrons. So what's the simplest thing that has electrons? What's the simplest atom that has electrons? Hydrogen. So although hydrogen is a bit of a pain, you should be able to make a hydrogen light bulb. Because hydrogen is very simple. A hydrogen atom consists of a proton and an electron. This is H1. H1 is the most abundant. H2 will have a neutron in there as well. So all we have to do is come up with some way of exciting the electron. So if we can excite the electron a little bit more, a little bit more, we should be able to excite the electron. And the electron's not going to stay excited forever because what's going to happen is it's going to absorb energy and then it's not going to stay excited forever. It's got to drop back down. And so eventually it's going to emit that energy. And it's going to emit that energy as light. So what we're going to do is we're going to excite this electron using electricity. Now, how do you get this to absorb electricity? One way we can get it to absorb electricity is like a lightning bolt. We're going to pass a lightning bolt through the hydrogen, but we got to make sure there's no oxygen, because if there's oxygen around, then you're going to get an explosion. The hydrogen reacts with the oxygen explosively. And so we're going to pass a lightning bolt through this. We're going to excite the electron. That's what happens in a lightning bolt. Do you see the white light from lightning bolts? Lightning bolt excites the electron in matter. That matter doesn't stay excited forever. Eventually those electrons will drop back down and start emitting light. And they emit all colors of the rainbow. So the concept is the same, except, a lightning bolt is quite jagged, like this, but essentially that's what we're going to do. We're just going to pass a lightning bolt through this and get it excited and have it emit white light. And that's just exciting electrons to all these levels and emitting. And if we have a continuum, which we would expect, we should get white light, because white light's going to require having all colors of the rainbow. If we have colors that are missing, then we aren't going to, it's not going to look white. There's going to be colors missing. So what happens is the electron gets excited. When the electron gets excited, it's either oscillating more or going faster, traveling faster. Or one way of thinking is it might be getting farther. The higher the energy, the further away the electron can be from the nucleus. This is like a bird. An electron's a bird, to fly farther and farther away, it's going to take more and more energy. The nucleus would be the nest. So how do you get a lightning bolt through hydrogen? Well, this is how you get a lightning bolt through hydrogen. What you do is you put hydrogen in a glass tube like this, and then you stick 2 electrodes, like 2 metal plates inside that tube, and then you crank up the voltage. There's a power source over here. A lightning bolt requires like tens of thousands of volts, right? Something like that, or 5,000 volts. I mean, you can calculate in physics. Depends on the gap you need to jump. Well, lightning bolt requires extremely high voltages because the density of the gas is quite high. Here, what we do is we put low pressure hydrogen in here. You put low pressure hydrogen, then you can get away with about 1,000 volts. And if it's low pressure hydrogen, it's not as jagged, because low pressure hydrogen is mostly empty space. The jaggedness comes from collisions and this kind of stuff. But this produces a nice beam. However, this beam is not white. So you crank up the voltage, and you can crank up the voltage to very, very high voltages and very, very high powers, but it still doesn't turn white. Like for my spatula, I just need to crank up the flame. Rather than using methane and air, I might try methane with oxygen. Air only has 20% oxygen, but if I had an oxygen cylinder that's close to 100% oxygen, that's going to burn more intensely. Or I could try other fuels. Rather than methane, I could try acetylene. Acetylene's going to burn even hotter. Anyway, so even if I crank up the power here, it still doesn't go white. It goes brighter purple. This light is purple. It's not white. And when you analyze this purple light, are all colors of the rainbow there? No, all colors of the rainbow are not here. There are only 3 colors, and they're very specific. There's a specific wavelength of red, a specific wavelength of green, blue, and violet. And all these are black. There's nothing here. This is what we call a discontinuous spectrum. And this discontinuous spectrum is called a line spectrum. Is it time or? 6 minutes, okay. Discontinuous spectrum, line spectrum. is what we get. And so the question comes up, why do we not see all colors? That's weird, because the situation is, if we think about the electron in the metal can get excited to any energy. You know, the more energy we input, the more excited the electron gets. But what this means is the electron in the hydrogen atom cannot get excited to any energy. So if we think of energy as speed, the electrons in metals can go any speed, from slow to fast. But the electron in the hydrogen atom cannot. There are forbidden speeds and allowed speeds. And so, in other words, here, there are forbidden energies and allowed energies. This is a continuous spectrum. And what was observed is this discontinuous spectrum, which we call the line spectrum. The line spectrum implies that there are forbidden and allowed energies for the electron. And the question comes up, why? Anyway, I'll stop here, 4 minutes early, since it's been long.